Hi, this is Miss Morgan again. We're going to do the second half of the weak acid practice problems. So we're starting at number 6. And number 6 asked us for the percent ionization of 0.10 molar acetic acid. Now, the percent of ionization is just the amount of the acid that ionized, basically compared to how much there was there originally. So, to get percent ionization, we need the value of X. Well, that came from the question 2, if you remember, because it was all about 0.1 molar acetic acid. So the ionization is going to be X, the amount that ionizes, divided by the original concentration, which is 0.10. Now, X from question 2, and there was a hint on your question sheet, X from question 2 was 1.32 times 10 to the negative 3 molar. So that divided by 0.10, our original concentration, and then to make it a percentage, times 100%, which gives us the answer of 1.32%. And there is our final answer. Continuing on with question 7. This one says tells us we have 0.10 molar HNO2. It gives us the information that Ka is equal to 7.2 times 10 to the negative 5, and asks for all the equilibrium concentrations. So this time we're going to set up we do have to set up an ice box. So our equation is going to be HNO2, which will be AQ, plus H2O, which is a liquid, in equilibrium with H3O plus and NO2 minus. Both of those will be AQ. Then the icebox, ICE, and I know a couple of people asked to go over this again. So remember, I is the initial concentration, and that would be for the HNO2 0.10. Water, being a pure liquid, does not appear in the equilibrium expression, remember? And then the ions at the very start, there would be no products, so they would be starting off at 0. Now, we say that we don't know how much it ionizes, so we call that X. So if X amount of HNO2 ionizes, then the change would be minus X for the HNO2. Water doesn't count. And then, as it's a 1-to-1 ratio, the H3O plus would be plus X, and the NO2 minus would also be plus X. So then E, the equilibrium concentration, we just work out from the two in here, 0.1 minus X. That would be what would be left at equilibrium from the acid. And then 0 plus X is X, and 0 plus X is X. So those are the equilibrium in terms of X. Next, write the equilibrium expression. So Ka is equal to the products, the concentrations of H3O plus and NO2 minus divided by the concentration of the acid. Okay, now remember, one of the things that we also try and do is to make the math as easy as possible, and because the equilibrium constant is pretty small, 7.2 times 10 to the minus 5, we're going to go with the approximation that x is so small that it'll have negligible effect. So this we're going to say is approximately 0.10. So our equilibrium expression now becomes 7.2 times 10 to the negative 5 equals x times x divided by 0.10. That gives us x squared is equal to 7.2 times 10 to the negative 5. I beg your pardon, 10 times 10 to the negative 6. 7.2 times 10 to the negative 5 times 0.1. And then take the square root. X will be 2.7 times 10 to the negative 3. Now remember, we have to check the 5% rule. So let's put that over this side in a box here. And that, for the 5% rule, we need to take the original concentration and multiply it by 5 over 100, and that gives us 5 times 10 to the negative 3. So comparing that to our answer of 2.7 times 10 to the minus 3, that's x is obviously smaller, so the approximation is okay. So finally, we need to actually write the answer to the question. So let x equal the concentration of H3O plus, which also equals the concentration of the NO2 minus. And remember, they were asking us about all the components, so we need to quote both of them. So that would be 2.7 times 10 to the negative 3. And don't forget, you've still got to quote the acid. So the concentration of the acid, and the concentration of HNO2 is going to be 0.10. So that there becomes our final answer. You've got to give the concentrations of all the components, and don't forget the units. Okay, question number 8 is asking about 0.10 molar HF, telling us that Ka is equal to 6.5 times 10 to the minus 4, and asking for the pH. So here we go again. HF AQ plus H2O liquid is in equilibrium with H3O plus AQ and F minus AQ. ICE for the icebox. The initial concentration of HF is 0.10, water again, and 0 and 0 for the ions. We'll say that X amount of the HF dissociates, so minus X, and it will create a change of plus X and plus X for the ions. The equilibrium concentration, therefore, for HF, the acid, is 0.10 minus X, and this will be X for the H3O plus and X for the F minus. Again, we're going to do the approximation, and so that say that x is so small that this will approximate to 0.1. Ka, H3O plus times F minus divided by HF. X times X divided by 0.10, and the equilibrium constant is 6.5 times 10 to the minus 4. That gives us x squared equals 6.5 times 10 to the negative 5, which gives us an x value of 8.06 times 10 to the negative 3. Okay, again, we have to check the 5% rule. So 5% is 0.10 times 5 over 100, which is 5 times 10 to the negative 3. Now, check to make sure. This time, if you notice, we've got 8.6 times 10 to the negative 3, and we've got 5 times 10 to the negative 3 is the 5% rule. X is bigger than 5%, which means we cannot use the approximation. We cannot use this number for x. So what do? We have to go back to where we made the approximation and put x back in and use the quadratic equation. So we have to go back to the point where we were at 6.5 times 10 to the negative 4 is equal to x. So we have to go back to the point where we made the approximation. So our equation becomes 6.5 times 10 to the negative 4 equals x times x divided by 0.10 minus x. Multiplying that out, we get 6.5 times 10 to the negative 4 times 0.10 minus x equals x squared. So now we have to distribute, so we need these two, which gives us 6.5 times 10 to the negative 5, and then these two, which gives us minus 6.5 times 10 to the negative 4 times x is equal to x squared. Rearranging that to get a equation that looks like your standard quadratic equation that you're used to gives us x squared, and then plus 6.5 times 10 to the negative 4 from here, and minus 6.5 times 10 to the minus 5 from here. Collecting everything on the same side, and that will make that equal 0. So now we've got a quadratic equation in the format where we can solve it. We've got a 1 here, that would be A. We've got 6.5 times 10 to the negative 4 x, there. That would be B. And then 6.5 times 10 to the negative 5, that would be C. So, using the quadratic equation, which, as you all remember, is x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. Okay, let's see if I can fit this on this last screen. Putting in the numbers, minus b is minus 6.5 times 10 to the minus 4, plus or minus the square root of 6.5 times 10 to the minus 4 squared, minus 4 times a, which is 1, times c, which is 6.5, times 10 to the minus 5, all over 2 times a, which is 1. Phew. All right. If you plug all that in to solve for x, you will find that x turns out to be equal to minus 0.0084 and 0.0077. Now, which of these two is going to be the right answer? Of course, it's going to have to be this one, the 0.0077, because the minus sign for x does not make sense. It would mean that we were adding acid. So that one, it can't be that. So from there, we're now back to knowing what x is. Let x be the concentration of H3O+. So the concentration of the acid ion, the hydrogen ion, is 0.0077 molar. pH is equal to minus the log of the H3O+, which is minus the log of 0.0077, which turns out to be 2.11. So after all that, we have found that the pH is equal to 2.11. All right, let's have a go now at number 9. That told us that we have 0.50 molar HClO2, and pKa is 1.92, and they want to know what the pH is. Okay, so if you're not sure about pKa, think about what pH means. pH means minus the log of the hydrogen ion concentration. Well, pKa means minus the log of the Ka. Minus log, that's the P part. pKa minus log Ka. pH minus the log of H concentration. So if we were going to work out that, we would do minus the log of Ka. But we know pKa, so we have to do the reverse. So the Ka is equal to 10 to the minus pKa. So if I want to figure out the Ka for the dissociation, I have to say it's 10 to the power of negative 1.92. And that turns out to be 0.012. So I know that Ka is equal to that, 1.012. And now we can do our standard icebox calculation. So HClO2 AQ plus H2O liquid is in equilibrium with H3O plus and ClO2 minus AQ and AQ. All right. I, C, E. The initial concentration of the acid, 0.50. Water, again, and 0 for the ions. Minus X is the change for the acid, and plus X and plus X for the ions. So 0.5, 0 minus X, and X and X. So from there we go on to our equilibrium expression, which is Ka is equal to the concentration of the H3O plus times the concentration of ClO2 minus divided by the HClO2, which becomes which becomes 0.012 is equal to x times x divided by 0.5 minus x. Now, I'm looking at the value of Ka, and that is not a very small Ka, where the approximations always are okay to do. So I'm going to go straight into the quadratic equation part of it, because I am pretty certain that the 5% rule would fail. If you want to, when we've done with this, you can try the 5% rule and double check me, but I think that I am going to go straight, as I said, into the quadratic. So this becomes 0.012 times 0.5 minus x is equal to x squared. That then we distribute, so we're going to end up with here and here, and that will give us 0.006 for the first part minus 0.012x is equal to x squared. If we rearrange that to get it into the more usual, what you're used to, that becomes x squared plus 0.012x minus 0.006 equals 0. So this is in the, here is A, so there's a 1 there. This is B, and that is C. if we put that into the quadratic equation, it actually comes out to be x is equal to minus 0.084 and plus 0.072. Which one is the answer that we're going to eliminate? It'll be the one that is negative. So our actual value for x is 0.072. So let x equal the concentration of the H3O plus, which in this therefore is 0.072 molar. pH is equal to minus the log of the H3O plus concentration, which is minus log of 0.072, which is 1.14. So our final answer is that the pH is equal to 1.14. And now for our last question, number 10. For this one, they tell us that the percent dissociation for acetic acid is 0.42%, 1 molar acetic acid. So we know that it's 1 molar acetic. And they tell us that the percent dissociation is equal to 0.42%. Now this is going to be a way of figuring out x. Remember that one of the first questions we did in this session was talking about percent dissociation. So remember, the percent dissociation is equal to x, the amount that dissociates, divided by the original molarity. Our original molarity is 1 molar. And then we take that, and that would be multiplied by 100 to make it a percentage. We know the answer to the percent dissociation. It's 0.42. So that means that 0.42 is equal to x divided by 1 times 100, which gives us x is equal to 0.0042. Multiply by 1 and divide by 100. So x is equal to 0.0042. Now we can use that in our icebox, or even straight into our equilibrium expression. And we can say that Ka is equal to the concentration of H3O plus divided by the concentration of the CH3COO minus ion divided by the concentration of the original acetic acid. So we have the concentration of the H3O plus ion will be X. The concentration of the CH3CO minus the acetate ion will be X. And the concentration of the acid will be 1.0 minus X. And we know the value of X. So this is going to be 0.0042 squared divided by 1.0 minus 0.0042, which comes out to be Ka is equal to 1.76 times 10 to the negative 5. And if you check your answer to question 2, I think it was, then you find that that is the same. Great. Well, there was a huge amount of rather complicated math. I think mainly complicated because of the weird numbers. They're not the nice round numbers that you are used to in when you do quadratic equations in math, but at least you now know that there was a reason for you doing it. So I hope you got on all right. If you have any questions, please either contact me or Mr. Morgan, and we'll be happy to help you out. I hope you're doing okay, and please let us also know if there is anything that you need. If you need a laptop or you need anything at all, please let us or the school know, and we will be happy to help you. Keep in touch, and don't forget we are doing ChemX on Friday. Hopefully we will see some of you there. Take care and stay safe. Bye.